Welcome everyone to another OCP Tap call. This is call number 141. It's my pleasure to introduce our speaker, Dr. Mason Marshall, a staff physicist in the NIST Ion Storage Group, where he focuses on precision metrology and fundamental physics. Dr. Marshall earned his PhD from Harvard University in 2019, where he carried out precision comparison of matters and antimatters. Following his doctorate, he held a postdoctoral position at the Smithsonian and the University of Maryland, where he developed detectors for search. Since 2021, he has been a key contributor to the development of NIST aluminum ion quantum logic clocks, which are the most accurate clocks in the world today. His work builds on two progress in atomic clocks research and the aluminum ion system he helped advance in setting records in both accuracy and stability, with profound implications for redefining the SI second. In his talk, Dr. Marshall will share insights into design, operation, and evaluation of his groundbreaking clocks, as well as the prospects of the future improvements and its central role in the upcoming international efforts to redefine the SI second. Please join me in welcoming Dr. Mason Marshall.
Thanks a lot. I'll talk today about our work on the aluminum ion quantum logic clock, which, as you mentioned, is currently the most accurate clock in the world. So I'm going to start off by talking a bit about what atomic clocks are, how they work, and why we use them. So I'll start out, though, with a brief overview of what we mean by a clock, since the answer can be different depending on who you're talking to. As a metrologist, the standard definition we use is that a clock is comprised of a frequency reference and a measurement device, where the frequency reference is something with a regular cycle, like swings of a pendulum, and the measurement device counts cycles of that frequency reference. The count of cycles and the frequency of the reference together give you a measurement of time. So a third important piece that I'll talk about today is what I think of as the clockwork in between these. It's whatever you need to convert the frequency reference into something that can be counted by your counter. So in the pendulum example, it would be all the gears and springs that go between the pendulum itself and the clock face, where you can count the ticks and measure the time. Now, I'm sure I don't need to sell a group that focuses on time synchronization on the importance of accurate frequency references, although I will talk a bit later about some of the applications of the kind of extreme accuracy we can get with clocks like ours. But frequency references have gotten more and more accurate throughout history, but for most of the time they've been based on specific physical objects, like the Earth's rotation, the pendulum in a pendulum clock, the balance wheel in a chronometer, or the quartz crystal in a quartz clock. So even though these get more and more accurate, they're all based on a specific physical object for each clock that's subject to variation from piece to piece, as well as degradation over time and other issues. The idea with an atomic clock, the basic idea is we don't want to use a specific object anymore, like your pendulum or your quartz crystal, as your frequency reference. We don't want to have a single quartz crystal in the, it's in its oven, and I think it was a 50-foot deep bowl that sets the time for the United States. Instead, we want to realize a frequency that's defined by the laws of physics. These laws are the same no matter where or when you look at them, and this gives a few big benefits over using a physical object, including repeatability, reliability, and precision. So what I mean by these are, for repeatability, if you build the same atomic clock at NIST or at PTB in Germany or at the NPL in the UK, your frequency reference will always tick at the exact same rate. For reliability, it won't drift or degrade over time unless there's something very wrong and very interesting about our fundamental understanding of physics, but that's a separate question. And then for precision, we can pick from our toolkit of modern physics experimental techniques and choose the system which we can measure more accurately than anything else. And so right now, the best systems we have like this are individual atoms. All atoms of the same type are exactly identical and unchanging based on everything we know about physics. The energy in an atom can only take specific values that are set by the laws of quantum mechanics and the atomic structure. And so the energy required to change the atom between these levels, in this example here, it's to move the electron from the 2 to the 3 shell, is set by these laws, and that sets a frequency that you can measure. So the most precise measurements that scientists can make right now are measurements of these atomic transition frequencies. Um, Now, for almost all the atomic clocks that we have today, the atom is what we call a passive frequency reference. And this is a difference from the pendulum clock, for example, where the motion of the pendulum physically drives the gears in the clock and ticks the clock forward. Passive means that the atom doesn't send out any signal or control on its own, and instead we need to go to it. So we do that typically by sending some electromagnetic radiation at the atom to interrogate this energy level transition. This is either a microwave signal or a laser beam, depending on the atom in question. If the energy in the radiation matches exactly the difference in energy between these two atomic states, then the radiation can cause the atom to make transitions, which we can measure. One way of thinking of this is to say the atom is like a very narrow band, very sensitive antenna looking for a very specific signal. If we can match our signal to this antenna, which exists in nature, then the atom will start to flip back and forth between these energy levels. So when our signal matches the atom, we call this being resonant or being on resonance with the atom. Now, the basic principle of atomic clocks is to turn the passive reference into a usable signal. We take the energy in the radiation, and which is defined by the frequency of that radiation, and we match it to the atomic transition. We do this in a feedback loop that's illustrated here. So this plot I'm showing on the left is the typical line shape or the bandwidth of the aluminum clock. We send radiation to the atom, and if it matches exactly, if it's right on resonance, then it drives lots of transitions. And if it's off, it's detuned, then we drive fewer transitions. And based on this measurement of the transition rate, we adjust the frequency of the laser or the microwaves to stay matched to the atomic reference. So we have to keep making these adjustments because the laser or the microwave or whatever is much less precise than the atom. It's going to drift and jump around. And we correct those drifts and jumps based on measurements using the atom. So what we end up with is a laser or a microwave signal that will always match the atomic frequency reference, even when the device generating the signal is imperfect. And we call this locking the radiation to the atom. And so the clockwork of an atomic clock is this feedback loop, which takes the atom as its frequency reference and generates locked radiation that you can then go to count to measure time. To see how this works in practice, to illustrate this a little bit, I'll talk about the cesium clock. So in the SI system of units, the second is defined as a certain number of oscillations of a microwave photon that's resonant with an energy level transition in cesium. At this unit is realized by the cesium fountain clock, which I've broken down here into the same three elements that we had earlier for the pendulum clock. The idea is the cesium atom itself is the frequency reference, with this ideal transition frequency set by the laws of physics being the thing we want to match. The clockwork then is the physics experiment, which generates microwaves, sends them into the cesium atoms, measures the transitions they drive, and adjusts the microwave frequency to match those atoms. The equivalent to the clock face on the pendulum clock is a frequency counter, which takes this microwave signal from the experiment and counts it to determine time. Now, this gets quite a bit more complicated when we go beyond just the frequency counter and think about how we actually use the atomic clock. I'm guessing many of you are familiar with the UTC and UTC NIST, which is the US's official instantiation of the International Atomic Timescale. UTC NIST gets distributed over GPS through the NIST Internet Time Service and over NIST radio stations. And that's generated by a whole bunch of devices that are calibrated by the cesium clock to keep them accurate. But for this talk, I'll focus on these two elements, the frequency reference and the clockwork, because that's what my research on the aluminum clock is focused on. So that's atomic clocks. I'll talk a little bit about optical clocks. So optical clocks use a laser beam instead of a microwave to generate the signal and lock it and propagate it to whatever useful device you have next. And so I'll explain why we use optical clocks, why are we moving away from cesium, and so on. So beyond using a fundamental system like cesium for reproducibility and stability, reliability, and so on, what makes a clock better or worse than another? And we focus on two basic metrics, the accuracy and the stability. There's a cartoon here from NIST that gives examples of being stable, accurate, and both. One way to think of this is, if you remember from high school or undergraduate science class, is to say that accuracy is basically the systematic uncertainty, and stability is basically the statistical uncertainty. A more colloquial way to describe first the accuracy would be to say it's the level at which you know that what you're measuring is what you want to measure. that you're measuring the unperturbed and unchanging frequency that's set by these laws of physics and the atomic structure of your frequency reference. So anything that changes the frequency you measure away from this ideal reference makes it inaccurate. This could be things like experimental problems, or it could be physical effects that change the tick rate of either the atom or the laser away from this ideal value. So when the media makes a statement like the aluminum ion clock is so accurate it would gain or lose less than a quarter second over the lifetime of the universe, what that means is that the expected accuracy of the clock will set a maximum degree of variation that you can expect between the frequency you're measuring and this ideal frequency of your reference. And that this maximum variation would add up to a quarter second over that 14 billion year period. Stability, on the other hand, is the amount of microscopic variation within the measurement of your clock's frequency. This determines the level of jitter in your system and also affects how fast you can average to a desired degree of precision. So when you're using the cesium fountain to calibrate all of the devices that produce UTC NIST and make sure they give an accurate second, the accuracy tells you how accurate your calibration is, and the stability tells how long you have to average to get a certain precision on your calibration. So which one of these you care about depends on your application. If you want to be sure that every single cycle of your system is the same, but you don't really care what that cycle time is, then you care only about stability. On the other hand, if you're going to run your system for minutes or hours or months and you only care about the total time elapsed, then you care about accuracy only. Most applications are somewhere in between with some demand on accuracy and some demand on stability. So why go to optical clocks? To answer that, I've broken down here the parameters that affect the accuracy and stability in a clock system. We see that both of these feature the frequency references transition in the denominator. One way to think about this is that no matter what your frequency reference is, whether it's a quartz crystal or a cesium atom or an aluminum atom, what we actually care about is getting out some useful signal, like a 1 pulse per second or a 10 megahertz signal to synchronize other electronics. So you're going to be taking your reference frequency and dividing it down to something useful. And in that division, preserving as much as possible the accuracy and stability of your reference itself. So if your cesium is operating at 900 gigahertz, or sorry, 9 gigahertz, and you want 10 megahertz, you're going to be dividing that by a factor of 900. So 1 hertz inaccuracy in your cesium clock is going to become 1 over 900 hertz, millihertz or so, inaccuracy in your 10 megahertz signal. And so what we're really interested in is this fractional inaccuracy and fractional instability. Then for the inaccuracy, the other relevant parameter is the uncertainty with which you can measure your transition frequency. And for the instability, we care about the SNR and the averaging time. Now, this transition frequency in the denominator is the driving force between going to optical clocks like aluminum. The optical frequencies that we use in our laser beam are something like 50,000 to 120,000 times higher than the microwave frequencies we use in cesium clocks. And so this, if we can measure these optical references to within even a few orders of magnitude of how well we can measure cesium, then we have a huge win in the fractional accuracy and the fractional stability. To illustrate that, here's a plot of clock progress over the decades since the development of the cesium clock. The cesium clock became the official second in the 1970s, and it's improved its accuracy by about 3 orders of magnitude since then. On the other hand, optical clocks have improved by more than 7 orders of magnitude in the last 35 years or so. And at this point, the best optical clocks have accuracy and stability that are 200 times better or more than the best cesium clocks. So there's actually a big international effort underway right now to redefine the second in terms of optical clocks to take better advantage of these measurements. And currently, optical clock performance, you can only evaluate your optical clock by measuring a ratio with another optical clock. Time itself is defined so much less accurately than an optical clock that just a measurement of your frequency is not actually meaningful. If we redefine the second in terms of optical clocks, then we suddenly gain all of that accuracy and precision in our measurements, which is important for basic science and for really demanding time applications. So I've marked here with a little star which ones of these are NIST aluminum quantum logic clocks. And you can see that they have, since they were first developed, consistently led the world in clock accuracy. So what are the applications of these super accurate clocks? Why do we keep building more and more accurate ones? One that's sort of close to my heart and my colleagues is for basic metrology for its own sake. So at NIST, our job is to advance measurement science and to provide to the US measurements that are as accurate as we can make them. And so that gives us an incentive just to keep pushing this accuracy. But beyond that, the second is especially important. So in the SI system, all of the other units are defined in part based on the second. For example, the meter is defined as the length that light travels or the distance that light travels in a certain amount of time. And to know that, you need to both have a measurement of the speed of light and also have a measurement of time to clock that by. And all of the other ones, except for the mole, which is just a number, all of the other ones are similar. So you cannot measure any other thing, anything anywhere more accurately than you can measure a second. Right now, the planned redefinition of the second is scheduled for 2030. And that is sort of assuming certain developments in atomic clock science in that time. But when that development is, when that redefinition is finalized, it lifts this cap on how accurately you can measure anything. Another thing is for fundamental physics beyond just metrology. So this is, again, important to my colleagues and me, very much so. The idea here is that these atomic clocks, we've made them the most sensitive and precise measurement instruments in history. And so if you're looking for these small variations or small changes that would help explain why our current theory of physics doesn't explain the universe, then you need to look at the most accurate and the most precise sensor you can get. One example is there are some theories that try to explain things like the presence of dark matter in the universe or the presence of matter at all, when, according to our current theory, it should have all just exploded with an equal amount of antimatter during the Big Bang. These like unexplained things, some of these theories predict, well, maybe the fundamental physical laws we measure now are not the same as they were during the Big Bang or during the formation of the universe. And so we can look for this time variation of fundamental constants. It should be so teeny tiny that you can basically almost never detect it. But atomic clocks give you a way to detect this because their precision is so extreme. There are similar theories that you can test with atomic clocks for dark matter, relativity, extensions, and other things like that. Finally, there's what I call the sort of practical applications. Beyond just increasing the precision of time itself, the measurements that we can get with atomic clocks could be used for something we call relativistic geodesy. Einstein predicted and experiments showed that a clock in a stronger gravitational field will tick more slowly than a clock in one that's got less gravity. And so by measuring the tick rate of our clock, we can tell how much gravity there is at the clock's position. And this tells us how much stuff, how much matter is between the clock and the center of the Earth. So you can use this as a measurement either of height very accurately or of the density of the Earth below the clock. And this has potential applications for things like oil prospecting or forecasting of magma flows and earthquakes. Another one is ever increasing GPS precision. So GPS is based on atomic clocks on satellites. And if you make those clocks more accurate, then you can make the timing and the positioning of GPS satellites more accurate, and all the applications that brings with it. Another one is precision navigation and timing without GPS. There you're doing things like counting the amount of time that's passed and your speed, or you're looking at the Earth's gravitational field as a map, or you're looking at the time between radio signals coming from Earth to a satellite. But all of that requires more and more accurate atomic clocks. So why aluminum? Aluminum is not a very exotic sounding element. The other atomic clock candidates like ytterbium or strontium or lutetium are all like fancy sciencey sounding things. But aluminum is currently the most accurate, and it's just something you see every day. Well, I'll break down a little bit the sort of aluminum clock as an intro to this. So the aluminum clock, the idea is similar to the cesium clock we had before. You have an aluminum ion as your frequency reference. And then our research in our group is this clockwork. It's the experiment that takes a laser beam, synchronizes it with the aluminum clocks, or sends it out of the aluminum clock, measures whether it's driving transitions or not, and synchronizes it. Also mentioned the cycle counter here is a device called an optical frequency comb. I don't have time to go into a ton of detail about that here, but you can think of it as a optical to microwave frequency converter, where the microwave's electrical signal comes from measuring the pulse repetition rate of a fast pulse laser that's synchronized locked to our clock laser. So that's how we get then this useful signal that can be divided down to generate a 1 pulse per second or a 10 megahertz reference or whatever you want. So here's the clock progress plot again that I showed earlier. And one question that you can take from this clock is beyond just different systems like the cesium clock or the aluminum clock or the strontium optical clock and so on, what changes version to version that makes the accuracy better? And the answer to that is if we look back to this equation for the clock accuracy, it's this frequency uncertainty. How small can we make this to make our clock as accurate as possible? We break this down into two factors. One is the line width, which you can think of as how selective the atom is about what radiation can cause it to make transitions. So a smaller line width means the atom is more selective, which means when you are making transitions, you know the frequency of your laser better. You know, it's within this little range that the aluminum ion or whatever your atomic system is, whatever that range it'll accept. The second thing is systematic shifts. So this is any effect which takes the frequency that we measure in a practical experiment and changes it from the frequency that we define for an ideal atom with no effects on it in free space, in the vacuum, at zero temperature, and so on. And so to sort of underline that, the SI system defines the second not just as a certain number of ticks of a cesium atom, but as a certain number of ticks of a cesium atom only when it's at zero pressure, at sea level, at zero temperature, and so on and so on. And so these effects which shift the frequency make the atom inaccurate. If they're shifting it away from this true value, we want to actually instantiate. Some examples of this are things like magnetic fields, the temperature of the trap in the apparatus creating black body radiation, the effect of the laser we use to do this measurement on the transition itself, the motion of the atom. So it's going to cause Doppler shifts, where just like a train going by and changing its pitch as it passes you on the station, and gravity itself, this relativistic shift I talked about a bit earlier. All of these are systematic shifts that we need to control, measure, and correct. And that's actually a huge part of what we do as atomic clock physicists, the control, measure, and correction of these systematic effects. So we want three things from our clock: a high frequency, a narrow line width, and a very selective transition, and low shifts. We want high frequency, we want narrow line width, and we want small systematic shifts. Now, aluminum hits all of these, and I'll talk about the transition we use in aluminum. We use this 1s0 to triplet p0. The symbols are not important for the rest of this talk, but we use this particular transition, which has a high frequency. It's ultraviolet. Its frequency is about 1.1 petahertz. So that's about 10 to the 15 hertz. Its line width is very narrow. It's only 8 millihertz that it accepts. This gives it a quality factor, or a Q factor, if that's familiar, of about 10 to the 17. It also, because of its atomic structure, has no shift from the trapping fields in an ion trap, which is crucial. It's also got one of the lowest shifts due to the thermal blackbody radiation of any clock that's been developed so far, and low shifts due to magnetic fields and so on. So it's got a high frequency, the highest actually of any clock that's yet been developed, a narrow line width, and low shifts. So now I'll talk a little bit about how the aluminum ion quantum logic clock actually works. We've got this system that has a really good candidate for being a clock, but how do we actually make the clock work? I'll start out by talking about our ion trap. So our ion trap is built from a lab-grown diamond wafer that's laser cut into a shape we provide, and then which has gold electrodes sputtered onto it over using a shadow mask. We do this to create what we call a radio frequency trap, or a Paul trap, that combines DC and radio frequency electrical signals to create the trap for the atom. We have titanium end caps, these two that are labeled end cap here. Those have a DC voltage on them, and that repels the ion away from the end caps and keeps it trapped in the middle at this trap chip. Then for the other two dimensions, we use the RF trap. These RF electrodes oscillate. We have a positive pole and a negative pole, and these switch back and forth at, in our case, about 70 megahertz. They confine the ion in the trap plane. And when we assemble the trap together, it looks like this here. We have the diamond wafer in the middle, sandwiched between some structural pieces with these end caps on either side. Now we need to use a radio frequency trap because there's actually a physical law that you can never have a stable electric field trap in all three dimensions at the same time. If you try and make an electrical potential, it will always have at least one direction that a charged particle will try to fly out of. We get around this by flipping the trap back and forth between these poles faster than the ion can actually fly out. The ion has some inertia and it has some rate of movement depending on the strength of the field and that inertia. And so if we flip the trap back and forth fast enough, the ion is stuck traveling in little circles or just balancing at the center. Here's a schematic of how the trap will flip back and forth between these two poles. The ion will try to fly out one way, but before it can get very far, the trap flips and it tries to run out the other way, and it never actually leaves. Here's a picture of what the fields look like at the ion during one of the two phases of this trap. And one of the crucial things here is you can see that it has zero field at the exact center. And then if it moves away from the center, it sees more field, and it gets pushed back by these fields until it's trapped at the center of the atom. It moves back and forth in this trap with two different frequencies. It's got a slow motion, seeing the average field going in sort of big circles around this. And then it's got a small motion, seeing the fast field wherever it's sitting at. These behave differently in a way that's important for making our clock accurate. The slow motion is quantized and can be cooled. It's basically the energy, the temperature of the ion. So one of the things you often see when reading about a laser-cooled clock or a laser-cooled experiment is it's cooled down to this many, whatever thousandths of a degree above absolute zero. And that's what we mean is the motion has so little energy. It's at a low quantum state. Then there's also this fast micromotion, which is driven by the radio frequency field. And that's got a very small amplitude because the ion is so heavy compared to these distances and fields that it just can't move very much, but it's pretty fast. So traps like this were first developed in the 60s, probably, 60s and 70s. And then the aluminum clock was first proposed in 1982. The idea of trapping an ion in one of these traps where it's nearly unperturbed. It sees very low field. It's in a vacuum. You can control the temperature and so on and so on. Trapping an ion in here and then using that as a frequency reference was proposed in 1982 by Hans Dehmelt, who went on to win the Nobel Prize for developing ion traps in the first place. So he proposed this. He called it the mono-ion oscillator, the idea that you could have one ion oscillating in the trap and being your local oscillator, setting the frequency of your time scale. He proposed this in 1982, but nobody actually was able to build an aluminum clock for 25 years after that, until 2007. And even now, there's only 4 groups in the world working on aluminum ion clocks. There's us, there's a group at PTB in Germany, and 2 groups in China. And so the question this begs is, why did it take so long when we knew that this would be such a good frequency reference to actually make one? And to answer that question of why is this so hard, I guess, is one way of thinking of it. I have to talk a little bit about something I've been glossing over so far, which is during this feedback loop, how do we tell whether or not we're matching the frequency of the atom? We say we're driving transitions, but what is the actual signal for that? How do we know? And so I'll talk about the cesium case to illustrate how this is done for most atomic clocks. The cesium case, the clock transition is a microwave transition between 2 energy levels in the ground state. You're essentially flipping the spin of the electron or the nucleus around. That detail is not super important, except to say that there are other energy levels that we can address in different ways, which are not part of the clock itself. So what we do is we apply a laser beam that will cause transitions from this ground state to some other level, but does so only if you're starting in a particular state. So it's basically, if the cesium atom is in this bottom state here, then you'll drive transitions to the electronic excited state. But if the cesium atom is in the top state, then it won't drive any transitions, it'll just sit there. We do this with a particular laser that we select to drive a very non-narrow bandwidth transition, a very fast and broad transition. If we're driving a transition that's like a clock transition, it's very selective about the radiation it accepts, and it will be very slow to accept that radiation and emit it. On the other hand, if we're driving something that's very strong, it will emit photons and fall back down very quickly. It emits a photon and falls back down because whenever in nature you have some high energy state, it's going to try to go back down to a lower energy state. It's going to try to relax. And in the atom's case, it does that by sending out a photon and going back to its ground state. So if you drive this very fast with a strong laser, you can be emitting lots of photons going up and down and up and down and up and down, and then measure those photons with a detector. So we do this and we essentially have a signal that says if this is bright, then we know we're in that lower state. If it's dark, we know we're in that upper state. And that's how we read out if we're making transitions. Another optical clock, strontium, works similarly. The current second most accurate clock in the world is a strontium clock that's just down the street from us. It's at the University of Colorado. It's got a similar structure to aluminum, so it's got some of the same advantages in sensitivity to some fields, high narrow bandwidth, high frequency, although it is much more sensitive to thermal radiation. Anyway, similar to cesium, you've got a second, less selective and fast transition that you drive for readout. You drive this up and it sends a lot of photons to your detector only if you started in this ground state. And that's how you tell what state you're in if you made a transition or not. Now, here's the aluminum clock transition again. This is ultraviolet at 267 nanometers. It's got a very long lifetime. Because it's so selective, it takes about 20 seconds for it to send that photon out. So if you were trying to measure using your readout laser, you would have to wait 21 seconds just to get one photon and hours to get enough to actually count with your detector. So that's impractical. Now, aluminum does have a strong transition that you could use to do the same readout that everybody else does, which would be great, except that it's at this 167 nanometer, which puts it firmly in the vacuum ultraviolet. That means that a laser beam here would get absorbed by Earth's atmosphere in about a few millimeters or centimeters of travel. You can't use that for your clock. So although the aluminum clock was proposed back in the 80s, it was impractical all the way through the 2000s because no one had figured out how to make a laser that you could use to read out these transitions. There's the third transition here to an intermediate state that is sort of in between these two. It's got a lifetime of 300 microseconds. So lots and lots of clock cycles and still impractical to read out just by counting photons, but it'll be important in a few slides. And now here I'll digress a bit to note that the ion storage group that I'm a part of doesn't just do clocks, but we also do trapped ion quantum information and quantum computation. And our group actually demonstrated the first quantum logic gate back in 1995. So after a few years of working with this quantum logic and also working with other clocks like the Mercury clock, we, and here I mean the collective we, because this is well before I was part of the group, but we had the idea that if we need this laser, which we can't build, to get this information out of aluminum, maybe another way to get it out is to use some of these quantum logic and quantum information techniques to transfer that information from the aluminum to something that's easier to work with. So, and it did turn out that building this vacuum ultraviolet laser was much harder, and it was easier just to build a quantum computer and use that to do the readout. That's sort of a joke, but sort of not. The technique that we developed to enable the aluminum clock, which is called quantum logic spectroscopy, is in a way the simplest possible 2-qubit quantum computer. I'll explain how we do that a bit. So suppose we start out with our aluminum in an unknown state. We've sent our laser to it. We're trying to synchronize that laser, and we want to read out whether or not we caused it to change states. So on this plot, we can see on the left the aluminum. It's got the ground state and the upper clock state, and we don't know which of those it's in. I've also marked here with the dotted lines the motion of the aluminum. Now in this trap, we've got a magnesium atom trapped together with the aluminum. We call that the logic ion that we use for this quantum logic. Because the electric force between the two of them is so strong compared to their size and distance, they're essentially locked together. They behave as a crystal and they move in conjunction with each other. And so the motion is shared between them. So we apply a laser beam that will add motion, but it does so only if the aluminum started in the ground state. And this way, it's kind of similar to that readout laser I was talking about earlier. You've conditioned this motion on the quantum state of the aluminum. And so this is entanglement. You've got a quantum variable, the motion, which depends on another quantum variable, the aluminum, and they can both be in a superposition of different states. They can be in either state without affecting the other, et cetera. So you've got this motion, but you'll notice that the magnesium also moved up. The motion is shared between the two. So we do the same thing in reverse on the magnesium. We use a laser which removes motion and changes its quantum state from bright to dark, depending only on the quantum state of the aluminum as connected via the motion working as sort of a bus. So then we can apply the readout laser to magnesium, and we'll see a lot of photons if and only if the aluminum started out in its ground state. So we've got this readout now that we use after this quantum logic entangling operation. This was first proposed for clocks in 2002, and quantum logic spectroscopy on aluminum was demonstrated in 2005. So we've been building clocks since then for about 20 years. Here's this same three-element breakdown with a little bit more detail. So for the frequency reference, we've got our trap, we've got our bright magnesium ion, and we've got our dark aluminum ion, which is in the space that's circled by the green circle. The only way we ever get information out of the aluminum ion is by quantum logic on the magnesium. Then in between this, we've got our clockwork, the experiment that generates the laser beam, synchronizes it with the atom, and sends it along to be measured. So rather than the sort of black box I showed before, here's one of our laser tables. The trapped aluminum is at the center. It's a little bit dark, but it's at the center of this table. And then we send to it 13 different laser beams along 7 different beam lines that we all combine to focus at the single point where the aluminum sits at the center of our trap. We use those to do the quantum logic, to do motional control, and to measure these systematic shifts that I was alluding to earlier, as well as to actually send the laser beam in. Once the clock laser is synchronized, we send it along to the cycle counter. I have here a little picture of one of the early frequency combs at NIST. I think the one today has a bit more optics and complication to give it better performance, but that's the basic, that's the idea. This is our clock comprises all of these elements. So at the start of the talk, we said the aluminum clock is the most accurate clock in the world. And so I'm going to talk a little bit about accuracy of the aluminum clock and how we evaluate that and how we get it to be the best in the world. So since the first demonstration in 2007, we've spent 2 decades refining different aspects of the aluminum clock. And we've iterated our trap designs and other aspects of our performance of our system to make significant gains in clock accuracy. And I won't talk about all these different designs. These are all different versions of our ion trap. But I'll point out that each generation has a few years or several years in between them. And each generation has between 2-ish and 10-ish factor improvement in accuracy. So I'll go through a couple of examples of systematic shifts here, because like I said before, besides the basic properties of aluminum, those are what set the accuracy of the clock. Measuring and controlling them is a big part of what we do as clock physicists. So the systematic shift with the largest uncertainty is what we call the limiting shift. And for the aluminum clock, every version has been the motion of the ion in the trap. This actually comes from Einstein again, this time his special relativity. He predicted, and more experiments showed, that a clock moving faster will seem to tick slower than a clock standing still. This is the source of the famous twin paradox, if you've heard of that, where a twin in space will age faster than a twin staying on the Earth. When the ion moves in the trap, even if its motion is incredibly small and close to the quantum ground state, it still will relativistically shift its time and the time it sees and the frequency it ticks at. And so we have to measure the motion and correct for this shift. So each of these traps was redesigned to reduce the amount of motion and to improve how well we can measure the little bit of motion that's left. So I'll talk about our process here. The first thing we look at when we're looking at these systematic shifts is to control the effect. In aluminum, we do that by cooling it down to 160 microkelvin, 160 millionths of a degree above absolute zero. This is about 5 or 6 quantum states above absolute zero. So I've got a little chart here of the motion that these 2 ions can do. In our trap, it restricts the motion into different axes, and they combine the two interact with each other. You can kind of think of them as attached to each other via a spring. And so they can sort of wobble or shake or stretch in different ways. We have to measure all of these. So after we can cool them as cold as we can, down to just a few quanta above absolute zero, the next step is to measure as well as possible. And so for the motion, we measure all 6 of these modes, and we measure them many times over the course of months to establish the uncertainty, the variability, and the accuracy of this measurement. So on the right here, I've got a plot of a series of measurements that was taken over about 3 months of one of these different modes. We measure them each separately. And then on the lower bottom, I've got a plot of the error bar on each of these compared to the number of quanta of motion in that particular mode. So once we've done our control and we've got our measurement, the last step is to correct for the shift. So here we either measure or calculate the effect on the clock of this shift. In this case, we call it the secular motion. This is the motion in the trap, and we can calculate the shift per amount of motion from Einstein's relativity, which is very exact and very well tested here. We calculate that, and we're left with the uncertainty from our measurement. And so this is what goes into limiting our accuracy, is that we can calculate the shift that our atom will see from its motion in the trap with a precision of about 4 parts in 10 to the 19. So I'll go through a second example, which is collisions with background gas in our vacuum chamber. This is another limiting shift, and one that we did a large amount of work on to correct, to improve in this version of the clock. So we have ions in the trap. When we want to start the clock cycle, we turn on our locked laser beam, and we want to see whether or not it matches the ion's frequency. We turn the beam on for 1 second, and during that time, the electron will be oscillating at its natural frequency, and the light will be oscillating at the frequency of its laser beam. So during the second, any frequency difference between these two builds up and builds up until at the end, if there's a 1 cycle difference out of the quadrillion cycles that have elapsed, you won't see transitions. But if there's a background gas collision, then partway through this procedure, the frequency difference builds up to a certain level, and then you've got a big transfer of energy. And that can scramble the cycles inside the atom. And the result you get out is different from what you would have gotten otherwise. So we can model the interaction that happens during this collision and put a limit on what its effect will be on the clock. It depends on the energy the background gas particle has. It has a large uncertainty. So we want to both measure and suppress these collisions. So we use the trapped ions as our vacuum gauge. We have them trapped in a particular order with magnesium on one side and aluminum on the other. And we can tell which order they're in by using a tightly focused laser beam. So we measure the rate of these collisions by looking at the change in the effect of our laser beam. And here we see that we see these collisions as big changes, these steep differences. So in our 2019 clock, we saw a collision about every 75 seconds. Now, our vacuum system that contains the trap is what sets this level. It's got a vacuum. You can see here our trap inside its vacuum chamber, and over here the chamber, including its connection to the pumps, the laser windows, and so on. To improve this, we made the chamber out of titanium. We added a bunch more pumps with better line of sight to the ions, and cleaning and processing it for about 6 months of my life, which might be why I like to pick this as the second example. So here's the 2015 version of this. We measure a collision rate of about 3 hours between collisions compared to that 75 seconds, which is a 150-fold improvement. And that suppresses the shift to a level where it's negligible at our current uncertainty. So this is our error budget overall. We do the same process for all of these. We go through every exercise to eliminate, minimize, or control the effect. Then we measure it as carefully as possible. And then we get the frequency shift either by a secondary measurement or by a calculation. And we correct the shift. So when we correct our atomic clock for all of these shifts, we say the measurement, the frequency we measure is shifted by about 6 parts in 10 to the 16. And it's inaccurate. The uncertainty on that shift is about 5 parts in 10 to the 19. That's what sets this maximum difference between our clock and the ideal frequency we see we want to model to make an accurate frequency reference. So getting the uncertainty budget for this clock took about a year of experimental work by our team after the system was already built and working. I'll talk a little bit about stability. I'm a little short on time, but I'll go through because this is also one of the big improvements we made on our clock. So the stability breakdown is here from this equation. And the key thing here is the signal to noise ratio. The averaging time is just how long you want to wait. And so usually we express this as stability per 1 second. And the transition frequency is set by your system. So some things that go into the signal noise ratio are this line width and the number of sensors you can put in a trap. Now, the number of sensors for our clock has traditionally been 1. Our big avenue of research now is getting that to more than 1, more like 8 or 10. And that would mean trapping 8 aluminum ions along with 8 magnesium ions. Now, this is one of the big avenues for improvement for ion clocks. They've traditionally been the most accurate, but not the most stable, and we're hoping to bridge that gap. But for the stability itself, the thing that we improved this time has been this line width. So our clock isn't the most stable in the world, although it is the most stable ion clock. It's within a factor of a few. So what this comes then is you build up this difference between your laser and your atom. So with the collision, your atom was getting shifted by the collision, and that jumbled things around. What happens more typically is your laser will be shifted just by the imperfection in your laser beam, and that will jumble things around. And so what we really needed to get our clock to be more stable was a better laser beam so that we could probe our clock for longer and have a narrower line width. And so we had a project. We're still in the process of building a more stable laser beam, but we thought, well, we've got this other clock next door at CU. It might be the second most accurate, but they do have the #1 best laser in the world. And so if we can just have them send that laser over here and use that, then that would be great. It wasn't quite that simple, but we send the laser underground through a 3.5 kilometer fiber. And we connect that using a bunch of measurements to stabilize that so that the clock doesn't get messed up whenever a truck drives over our fiber. And we connect those with 3 different frequency combs. And we get out a laser that we can use to control our clock laser and send to our atom. And so here's the diagram of this whole process. I'm not going to go into this at all, but here's the simplified one. We have the laser over at CU. We send it to our comb, and we synchronize our laser to it and then probe the clock. And that lets us go from about a 10 hertz line to a 1 hertz line. It improves our stability by a factor of about 3 over the previous clock, which gives us a factor of 10 improvement in averaging time. And this is the best for any ion clock. The best clocks, the most stable clocks, have thousands of atoms. They're optical lattice clocks. But even with only 1 ion, we can still be within a factor of a factor of order less than 10 of the stability of the best lattice clocks, and are aiming to bridge that gap with more ions in the future. And so with that, I'll say thanks for your time. I'll credit my team, our grad students and colleagues at NIST, and I'll be open for any questions you have.
Hi there. My name's Phil from Open Lunar Foundation. Great presentation. I put a question in the Q&A here, but I'll just ask
okay.
it now. Would exposure to high energy particles like solar wind or cosmic radiation, like at Earth's surface, the stuff you can see in a cloud box or whatever, would that cause artifacts similar to the gas particle interactions that you alluded to before and could measure?
Yeah, so there's 2 ways that could happen. One is if one actually just hit our atom, and then it would just look like a gas particle. Another one would be if you have some radiation, like a ion traveling through, or like a cosmic ray that scatters. I guess that would be the main thing, would be like if it scatters off something. You could imagine that if the radiation is close to the frequency the atom looks for, it would disturb that also. I think that just statistically, those events are going to be much less likely for a background gas than a background gas collision, even now that we've got our 150-fold better vacuum, just because the volume over which the atom is sensitive is so small. But you can imagine that being a bigger problem with the number of atoms. So yeah, I think that at some point, as we get better, one of the things with these is as you get more and more accurate, you end up needing to look to new effects and characterize things that were previously negligible. And so at some point, someone's going to have to calculate the rate of those, and also background radiation from like trace radioactive elements in your vacuum chamber, right? All this stuff they have to deal with for the big detectors that are kept in a mine underground, and so on and so on.
I'm thinking about
eventually
outer space, right? Solar wind,
Oh yeah,
outer space.
space,
So that's
right.
where most the
So
charged
yeah, in
particles I
space,
see.
then I know that you get orders of magnitude more of these, right? And that's something I think that you'd have to calculate.
Right.
There are atomic clocks in space now, They are much less accurate. I think they're all microwave clocks, so they're at the 3 or 4 orders of magnitude less accurate than this one. But at some point, that's going to be an effect that needs to be worried about. Yeah.
Quick question, Mason. How is this whole technology, I mean, with the aluminum ion clocks, serving for the miniaturization? Are we like getting, let's say, more options? Let's say moving from small vapor cells or going toward MEMS, perhaps?
Yeah. So the vapor cells, there's actually, I think the lab next door to us works on developing a chip scale optical clock. And there they have not a vapor cell, but a in-chip beam.
Awesome.
And so they've got like basically they have a laser which heats up a gas repository and that makes a beam through a collimator. And so that's
Mhm.
very cool. And so that's sort of going towards some of this increase in accuracy you can get over microwave clocks. You have like a built-in little laser diode and a built-in photodetector. Taking the aluminum clock there is probably a couple of decades or maybe 15 years. The thing
Mhm.
that people are working on right now at PTB in Germany, their aluminum clock is less accurate than ours, but where they are ahead of us is on a portable aluminum clock. They're building one that's about the size of a RV. It's in a
Yeah.
trailer that they pull behind a pickup truck. And so that's where we're at for miniaturization right now for like these really cutting edge 10 to the minus 18 or 19 optical clocks. But
Mhm.
the technology is being developed on the way there for getting optical clocks into an applicable and portable domain.
Yeah. Yeah, I mean, I'm trying. I like to see like how far are we where with, let's say, probably, as you said, probably 2 decades or something, where we will have a MEMS based, like, it can be an optical clock, whatever it is, like something with, let's say, 10 to the minus 15, like further, where you have like super good holdover, and then like when you go from outdoor to indoor, your positioning
Mm-hmm.
remains, let's say, within millimeters, and you have like this technology so well that is like ubiquitous, where, let's say, you will see the next, I don't know, iPhone or Android, whatever, being advertised with it. That's what I'm
Mm-hmm.
thinking about. That's why I always look forward for
Yeah.
this technology to see how far we are.
So one of the key challenges for that is something that we're working on, not in my team, but in the quantum computing team that's part of our group, is integrated photonics. And
Yes.
so we have a laser table, right? But if you need beams from at least 3 directions. You can't just have one LED for a really cutting edge clock. You need to be able to measure these motions in 3 dimensions.
Mhm.
And so being able to deliver that with a chip with gratings that it can be fabricated in a normal fabrication facility would be a huge step towards a miniaturization of this stuff. You could turn that whole laser table into like the size of your watch or smaller. And so that's a project that's active. One thing that is sort of outside of us is the UV lasers. So ultraviolet lasers are necessary to get the most out of these clocks because you want this large denominator, but
Mhm.
they're quite a bit harder to make than telecom lasers in the infrared. And so that's something that I believe some of the bigger industrial companies are working on, especially in the context of UV and extreme UV for silicon fab,
Yeah. Yeah.
which is the other place where these wavelengths are used.
Mhm.
But that would have to be miniaturized to be able to take an aluminum clock out of the backpack or electronics rack size and into something that's truly like miniaturized.
Yeah. 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 Great. Yeah. Any more
Mason,
questions? Yeah.
could you comment on how these clocks compare to the nuclear clocks in terms of accuracy and stability? I know there's a lot of noise around nuclear clocks recently. They also need UV
Yeah,
lasers and such.
yeah. So the nuclear clock is, in one sense, like the aluminum clock on steroids. It's got a very high frequency and it's got a very hard to make ultraviolet laser beam. So they are actually using the demonstration that's been done so far is using a vacuum ultraviolet laser beam, and they did spend multiple PhDs to make that laser. The other thing, though, is there's some unknowns. So the sort of the maximum upside of the nuclear clock is more accurate. You could get a more accurate clock because you've got this higher frequency, and also because since it's in the nucleus, it's shielded by the electrons from some of these systematic effects. On the flip side, there's a lot of uncertainty about that because no one's actually been able to make these measurements very precisely, right? So far, it's only been measured where you make a crystal that has some of the thorium is the isotope that's used. It has some thorium in this crystal, and you measure it, and that's very affected by the vibrations of the crystal and the effects of the other atoms and molecules in the crystal, and so on and so on. So there are some potential systematic shifts that just aren't very well understood yet, especially when you get into nuclear physics, where you can't even calculate it with a supercomputer because the systems are so complicated. One of the things that the nuclear clock will definitely be better for is some of these new physics searches, because it's much more strongly affected by different types of dark matter that may or may not exist, or different types of new forces. It's much more strongly affected by those. So even if you have a nuclear clock that's not as accurate as the aluminum clock, you can still probe this new physics much better. As far as what's eventually the best, most accurate clock, the nuclear clock has a good shot, but it's just uncertain at this point.
Oh, thank you. Yeah, that was great.
Wonderful. Any more questions from the audience? Okay, if none, we'll adjourn this call. And again, thank you again, Mason, for this fantastic educational presentation.
Thanks so much. It's fun to give a talk, and I'm happy that you guys were
Very
interested.
welcome. Pleasure is on our side. And we'll see everyone in 2 weeks for a talk by Jason Rock from Dell about NICs. All right? Great. Bye, everyone.
Thanks.